This is recitation 5. And we will talk about capacitors today, the capacitors. Recitation 5, capacitors. We need several formulas to work with the capacitors. And first of all, we will introduce the capacitance. By definition, capacitance C is charge Q divided by the difference in the electric potential, and we take absolute value. Now, how to find the difference in the electric potential? We will use this formula, V at R2 minus V at R1 is equal to minus integral from R1 to R2 E dot dr. How to find the electric field? We will find the electric field using Gauss's law. Integral closed surface E dot ds. So flux out of closed surface is equal to the charge enclosed by this surface divided by epsilon naught. So we will use these three formulas to find capacitance of different for different capacitors. And first of all, for problem 1, we have a parallel plate capacitor. The area of the plates is given. Let's call it A. And the distance between the plates, let's call it D. D is also given. So D is small. I obviously did not draw it up to the scale. What we need to find? We need to find the capacitance. The capacitance, by definition, is charge divided by delta V, difference in electric potential or voltage between these two plates. So to find the capacitance, this capacitance C, I will charge this plate with the charge plus Q, and I will charge the plate that faces this one with charge minus Q. So there are two parallel plates facing each other. Charge is uniformly spread. I need to find V at D minus V at 0. So let me have x this way. This is 0, and this point is x equal to D. I find V at D minus V at 0. This is equal to minus integral from 0 to D. And then electric field. Electric field is so far unknown. I put E dot dr. We need to find the electric field from Gauss's law. I need to find out what will be our Gaussian surface. Gaussian surface for this plate, I will choose a cylinder. Part of this cylinder will be inside this plate, and another part will be outside. So this is imaginary surface, a cylinder. Now I need to find the flux out of this surface. Flux E dot ds will be equal to Q enclosed over epsilon naught. Flux out of this surface will be 0 because the electric field inside conductor is 0. This is conducting plate. This is a capacitor. I have two conducting plates. So electric field inside the conductor is 0. Flux out of this side is 0. Flux all out of this side surface, banded surface of the cylinder is 0 because the electric field is along x. This is the electric field. And area vector will be perpendicular to this electric field, so flux is 0. And we have non-zero flux through this cap of this imaginary cylinder. The flux out of this side of the cylinder will be, the electric field will be parallel to area vector, so dot product will be just product. Electric field from symmetry is constant. I take it out of this integral, and we just discussed that integral ds will be just this cap, which I will call A. So A, let's use a different color. A is area of this cap. I'll put it like this, A. Okay, so EA is our left-hand side of the of Gauss's law, and right-hand side is charge enclosed. So charge enclosed is just on the surface where the cylinder comes out of this parallel plate. So let me draw the side view. So if I look from a side, this is my cylinder, and I'm looking for the charge right on this surface. That's where the charge is enclosed by this cylinder. And this charge is sigma, charge per unit area, which in my case is Q over A. So it is 1 over epsilon naught. I just rewrite it. And then it is sigma, charge per unit area for the whole plate, times area enclosed by the cylinder, which is A. So, of course, electric field does not depend on our choice of Gaussian surface, and we find the electric field between the plates of this capacitor as sigma divided by epsilon naught. This is the electric field. If I express sigma in terms of Q and A, I will get sigma is Q over A, and epsilon naught is still here. This is the electric field. Now I bring this electric field here, and I find the difference in the electric potential. So it is minus integral from 0 to d. E dot dr is simply Ex dx. Electric field is constant. It is Q over A epsilon naught. So integration is trivial. Dx. This is Ex dx. I take these constants out of integral, minus Q divided by A epsilon naught. And then integral dx is x. I plug in upper limit, which is d. Lower limit gives me 0. This is V at d minus V at 0, difference in the electric potential. And now I can find the capacitance. Let me bring this d a little bit lower, and I'll keep writing here. So this is Q divided by delta V, absolute value. Absolute value of delta V is QD divided by A epsilon naught. So A epsilon naught come to the numerator, and then Q and Q cancel out. What we have is A, area of the plate, epsilon naught divided by distance between the plates. So as expected, the capacitance depends just on the geometry of this capacitor, on the area of the plate and the distance between the plates, and does not depend on difference in the electric potential.